Good day, my fellow students. I am Kerwin, and in this segment, we will be learning about rocks and minerals. Now, what are rocks and minerals? Rocks and minerals are like the building blocks of our planet. They form the foundation of our planet and provide important resources. They also shape like landscapes. They also provide us with important materials like metals and gems. By studying rocks and minerals, we can learn about Earth's history and how it has changed over time. This helps us understand natural events like earthquakes and volcanoes, and even predict future changes.
Now moving on to our first segment, we will be learning on how to identify rock minerals by its chemical and physical properties. First, we are going to identify these kinds of rocks by their physical properties. Let's get started. Different minerals can share the same color, and the same mineral can appear in different colors. But color alone isn't enough for accurate identification. Identifying minerals by color isn't reliable because impurities can cause variations. The streak of a mineral is the color of the powder it leaves when rubbed on unglazed porcelain. This color can differ from the mineral's surface color. Philosophy describes how a mineral's surface color reflects light. Influenced by its atomic structure, it can be classified as metallic, such as pyrite, or non-metallic, such as quartz.
Hardness measures a mineral's resistance to being scratched using the mass hardness scale. This scale ranges from talc, softest 1, to diamond or hardest 10. Cleavage is a mineral's tendency to break along specific planes, creating smooth, reflective surfaces. It occurs along lines of structural weakness. Fracture refers to a break in a mineral that isn't along a cleavage plane. Unlike cleavage, fractures aren't determined by the mineral's structure and can vary. Minerals without cleavage break in all directions when struck. Gravity. It is the ratio of the weight of a mineral to the weight of an equal volume of water, indicating how much denser the mineral is compared to water. Lastly, the crystal shape of minerals reflects their internal atomic structure. While all minerals are crystalline, only some display their crystal forms, which develop the mineral that has space to grow. That's all for understanding on how to identify rock minerals by their physical properties. Let's take a recap of the 8 properties. First, we have the color, strength, luster, hardness, cleavage, fracture, specific gravity, and crystal shape. Now for the chemical properties of the rock minerals.
We have identified 2 factors in order to know what type of rock minerals by its chemical properties. First on the list we have is reaction to certain chemicals. Rock minerals react with certain chemicals like calcite, which fizzes with 5% hydraulic acid due to CO2 release. Calcite can also be identified by hardness, luster, and cleavage.
Also, there are 2 chemical properties that we need to understand how the rocks react to chemicals. First, we have a solubility. Solubility refers to the ability of a substance to dissolve in a solvent at a given temperature. For instance, biotite, a common mineral in igneous rocks, dissolves in both acidic and basic solutions, releasing its floating potassium ions in the process. Second, we have a melting point. The melting point is the temperature at which a solid becomes a liquid. Minerals with lightly bonded atoms in their crystal structure have high melting points.
Second on the list is we have magnetism. This can be tested by seeing if a small magnet responds to the mineral. The most common mineral that is strongly magnetic is the mineral magnetite. Magnification may be required to see striations in magnification, cleavages, and surfaces. There are different kinds of magnetism. Minerals may be ferromagnetic, diamagnetic, or paramagnetic. In ferromagnetic minerals, the moments of a mineral's electrons are aligned in a constructive way, and the minerals have properties similar to those of a metallic iron. Diamagnetic minerals exhibit little magnetic character overall but may be weakly repelled by a strong magnetic field. Paramagnetism, which means it is attracted to a strong magnet.
Now let's move on to the next segment.
Supriya, and in this segment, we're going to talk about crustal deformation. But first, let's talk about tectonic plates. Tectonic plates are big pieces of Earth's outer layer. They fit together like puzzle and cover the whole planet. These plates float on a softer layer below them, which let them move around slowly. Plate tectonics developed between 1950s and 1970s, built on the concept of continental drift. It states that Earth's lithosphere is divided into plates that move on a molten asthenosphere beneath. These plates interact in various boundaries, coming together or moving apart. What are the types of boundaries where these plates interact? The first type of boundaries is convergent boundary. This is where two tectonic plates collide, resulting in mountain ranges, subduction, volcanic activity, and earthquake. Notable features include the Himalayas and Andes Mountain. The second type is divergent boundaries. These occur when two tectonic plates move apart, creating a new crust from molten magma. There are two types, oceanic and continental. They are linked in volcanic activity, shallow earthquake, and significant changes in Earth's surface. And the last type is transform boundaries. These involve horizontal movement between tectonic plates, resulting in lateral displacement and crustal deformation. Key features include shallow earthquake and fault line. They occur both on land and underwater, link mid-ocean reaches and subduction zones. Who first proposed the idea of plate tectonics? Alfred Wegener, a German meteorologist, proposed the idea of continental drift in 1912, suggesting that a supercontinent called Pangaea once existed. Over time, Pangaea broke apart, leading to the formation of today's continents. He published his theories, The Origin of Continents and Oceans, in 1915. And now, let's talk about the crustal deformation. Crustal deformation refers to the changing Earth's surface caused by tectonic forces that are accumulated in the crust and cause earthquakes. When rocks are stressed, the resulting strain can be elastic, ductile, or brittle. This change is generally called deformation. Elastic deformation is a strain that is reversible after the stress is released. For example, when you stretch a rubber band, it elastically returns to its original shape after you release it. The type of deformation a rock undergoes depends on pore pressure, strain rate, rock strength, temperature, stress intensity, time, and confining pressure. And that's the end of this segment. Thank you!
Food stalls, fresh goods, unique products, you can find those in the marketplaces of Quezon City. The marketplaces in Quezon City, like Litex and Commonwealth Market, are lively spots where you can find fresh foods, local foods, and unique products. They support local farmers and vendors, making them important for both the economy and local culture. It highlights the resilience of small businesses that thrive despite competition from larger retail chains. These markets encourage a sense of community, where residents actively support local vendors by choosing to buy fresh produce, artisanal goods, and unique products. Many vendors wake up early to source fresh produce or prepare their goods, reflecting a strong work ethic. Their day often involves not just selling, but also engaging with customers and adapting to changing demands. These individuals are deeply connected to their communities, probably balancing their market work with family responsibilities. Their hard work contributes to the vibrant atmosphere of the markets, making them essential to the social and economic structure of the area.
Now let's move on to the next segment, where we'll explore the exogenic and the endogenic processes involved in rock formation.
Geomorphic processes are the natural mechanisms that shape and alter the Earth's surface. Exogenic and endogenic processes are responsible for geomorphic processes. Exogenic processes are surface processes that are driven by external forces from the Earth's atmosphere or surface. They involve the breakdown, transport, and deposition of the materials. Three main types are weathering, erosion, and deposition influenced by the agents like wind, water, waves, and ice. Weathering is a process by which the Earth's surface or the subsurface rocks disintegrate, dissolve, or break down. It has shaped the landscape over time by wearing away rocks and soil. Rocks at the Earth's surface are exposed to physical and chemical weathering processes. Physical weathering breaks down rock without chemical changes caused by temperature changes, abrasion, salt crystals, and frost action. Chemical weathering alters a rock's composition through interaction with air or water, like oxidation or dissolution. Erosion is a process by which weathered rocks and soil are transported away. Natural forces, primarily water or wind, move these materials to new locations. Water commonly carries sediment while wind blows particles away. Glaciers, though slow, can also pick up and transport significant amounts of earth materials. Erosion occurs through three main methods, which is water transport, wind transport, and ice erosion. Water transport involves the movement of sediments through traction, saltation, and the transport of fine particles and soluble salts. Millions of tons of sediment are carried daily along rivers, coasts, and oceans. Wind transport shapes stunning landscapes by moving sand, creating dunes in deserts. However, it can also lead to sandforms and erode topsoil on farms. Ice erosion happens when moving glaciers pick up particles and transport them downhill, or when friction between the ice and bedrock erodes materials that are then carried downhill. Gravity helps transport loosened, weathered materials downhill without needing water, wind, or ice. This gravity-related erosion is a key factor in mass wasting events. Position. When weathering occurs, tiny pieces of the earth are not lost. Instead, they are moved through erosion and deposited everywhere. Deposition is a constructive process that places weathered and eroded materials in a new location, often by agents like wind or water. This process changes the shape of the land. Sediment can accumulate in layers in water bodies or as piles left by glaciers. While deposition typically occurs in water, it can happen in other environments as well. The accumulation of deposited materials shapes landscapes and creates various landforms, such as floodplains, formed by fluvial deposits, and sand dunes created by wind.
Endogenic forces refers to internal forces that are present in the Earth's interiors. It is the pressure that comes within the ground. How do these volcanic eruptions relate to the endogenic process that works beneath the Earth's surface? Magmatism shapes Earth's evolution by forming mountains and adding new materials. Magma forms from the partial melting of rocks in the mantle, continental crust, or oceanic crust. When magma erupts, it is called lava. Rocks melting in subduction zone and heat in dark melting at hotspot create magma. Volcanism happens when magma erupts as lava, ash, gas, or rock fragments. This process forms different volcanic landforms. Igneous rock form when molten rock cools and solidifies. Metamorphism occurs when rocks are deeply buried and subjected to high pressures and temperatures. This changes their structures and compositions without melting. The rock cycle explains how this process forms and transforms Earth materials. Now, let's move to the next segments. We will explore the history of Earth.
Studying Earth's history reveals a dynamic planet with fields like paleogeography, paleontology, paleoecology, and paleoclimatology, exploring ancient landscapes, organisms, ecosystems, and climates. The geological time scale acts as a calendar for these transformations, categorizing Earth's history into aeons, eras, periods, epochs, and ages. Aeons are the longest time intervals, with three recognized: the Proterozoic, Archean, and the Phanerozoic. The eras, the GTS as defined by the International Union of Geological Sciences, includes 10 specific intervals, ranging from the Archean, which is 4 billion years ago, to the Cenozoic, which is 66 billion years ago, up to the present. Periods represent significant time frames during which specific rock systems formed, determined through stratigraphic sequences and paleontological data. Epochs are subdivisions of periods. It is often used to denote distinct geological time frames, particularly within Paleogene, Neogene, and Quaternary periods. Stratified rocks or sedimentary rocks serves as historical evidence, revealing timelines of geological events and ancient environments that is determined through several methods. Relative dating, analyzing the position of rock layers based on the principle of superposition, where older layers are beneath younger ones. Fossil correlation, using fossils to establish relative ages by comparing them across different locations. Radiometric dating, measuring the decay of radioactive isotopes in rocks for precise dating. Magnetostratigraphy, studying magnetic properties of rock layers to estimate ages based on their known magnetic field reversals. And lastly, biostratigraphy, analyzing fossil distributions to correlate and date rock layers. Index fossils, these are species that live during specific periods and are crucial for defining geological time subdivisions. By locating these index fossils, geologists can accurately date and correlate rock layers across various regions, enhancing our understanding for our Earth's history. The GTS provides a structured timeline reflecting major biological and geological events. allowing scientists to interpret changes in Earth's condition, such as mass extinctions. By studying rock layers, scientists construct past environments and the evolution of life, illustrating how our Earth has changed after billions of years.